All right, guys, this is a quick overview of the beginning of momentum for anybody that potentially may have missed it. So let's start. Okay, so the chapter that we're going into is really quick because it's relatively small, because it's really an extension of something else we've already done. There are three main ways to describe motion, of which we've done already. Kinematics, I'm putting 2D kinematics in that as well. We have forces, and then we just finished energy. Okay, this is actually going to be an extension of forces. So very briefly here, we're going to review stuff that we remember from forces. Okay, so Newton's first law was basically if you have a balanced set of forces, that's your cause, then it results in a constant velocity or zero acceleration. So essentially, if your net force is 0, then acceleration is 0, and velocity is constant. Now, the reason you didn't see that particular equation or any sort of equation like that in that chapter is because that fell into the second law, which was, of course, if forces are not balanced, then there is an acceleration and velocity is changing. And we incorporated that, instead of writing all this out, we incorporated that in with how we calculate that acceleration. And that was if there is more net force, we increase this, then acceleration will also increase. And if we increase mass, acceleration will decrease, because that's one of the properties of mass. Bringing up, by the way, the two properties of mass, which are mass has gravity, meaning all mass attracts all other mass, which we see in this equation right there. More mass means more gravity. Okay, and the second property, that all mass wants to stay going at a constant velocity, or more mass wants to accelerate less, which we have already seen in that particular equation right there. Now this equation is usually rearranged. Typically we don't see it like that. Typically we move the acceleration over and we get this right here. And like I said a second ago, that's equation right there is where you see this. If there is zero acceleration, that cancels out, showing us that net force is 0. So you'll notice that a lot of that stuff that we just said about Newton's first, Newton's second, and the property of inertia are all nicely wrapped up into that equation right there. That's really Newton's first and second. Newton's third law was for every force, if I have a force of object 1 on 2, there's an equal force of 2 on 1, and it is in the opposite direction. Okay? When you look at chapter 4, what you'll note is that we spent most of our time on this equation right here, because this equation involved just a single object. And you can remember that we did force diagrams, a lot of force diagrams of just a single object to do this right here. There were a few instances that you might remember of us looking at this law, but it usually revolved around when we had two objects, like in the lab when we looked at the sliding mass versus the mass that was hanging. There was a tension that was on both of them that abided this law, but again, you're not going to see this until you're dealing with multiple objects. So this chapter, okay, this chapter is really an extension of chapter 4, okay, which is why, like I said, it can go so quick. This chapter is called Momentum. You've probably heard of momentum before, and honestly, momentum is just a different perspective, kind of makes sense, of that chapter right there. So, what is momentum? Momentum is a value that is a combination of two things that we have previously discussed that kind of makes sense that they go together. Firstly, we put mass, specifically the property of inertia right here. And we think, okay, what vector best goes with inertia? Well, inertia is an object's ability to stay going at a constant velocity. So let's put that vector of velocity with it. So velocity is the vector, mass is the scalar, and essentially what you get here is this. Imagine that you had two people, a child and an adult, walking down the road at the same velocity. Well, if we compare their velocities, they're not going to look any different. But if we multiply them by the scalar of mass, we get a different vector. Okay, so let's say I multiply them by some mass, which would take this, and when you multiply by a vector by a scalar, it basically just extends it. So we'll just say, hey, here's the momentum of, say, the child. Okay, that's maybe hard to see there. That should be make momentum of the child. Okay? Now, if the adult has twice as much mass, even at the same velocity, you can see their vector, their momentum vector. Oh, I forgot to mention this. Yeah, strangely, the letter used for momentum is P. It's Latin. Progress. I don't know. Point is, it's P. So you've got the adult here going at the same velocity as the child, but due to having twice the amount of mass, is a much larger momentum vector. And this kind of makes sense because obviously we would expect the adult to be much, much harder to stop. Now, usually when dealing with this over in forces, we have to deal with this kind of as two entirely separate pieces, kind of with mass and acceleration and changing velocity within the acceleration. So this allows us to kind of put it together all at one point in time. Okay, let's address a couple things, real small. Firstly, units of momentum. Well, if we just do our unit analysis thing, look at the right side, we know that that is kilograms. We know that that's meters per second. So the units should be kilograms, meters per second. Now, usually at this point in time is where I show, hey, this is, scientists are lazy and they call this something. They don't. I don't know why they don't for momentum, but those are, in fact, the units for momentum. As I said a second ago, momentum is a vector. I believe it is the fifth vector that we've discussed with displacement, velocity, acceleration, force, and now momentum. Just a quick reminder that you can't really combine different vectors in like a vector addition. They really have to be of the same type. That's why I drew a velocity and these momentum vectors in entirely separate colors. They don't usually belong together. As a matter of fact, I'm pretty sure most textbooks just pick a color and stick with that for every single time they use that particular vector. I don't pay attention that close, but that would kind of make sense. All right, so I want to show you really how this section of momentum is directly connected to that. And to do that, I'm going to start right here at Newton's second law. So we're going to look at Newton's second law and simply see how does this kind of look like momentum. Okay? For starters, acceleration's definition is the change in velocity over time. So if I take this equation and substitute that in instead, you can start to see, I don't know if that's really close to that momentum thing over there. As a matter of fact, we're going to go ahead and take time and move it over. And mass times the change in velocity actually results in the change in momentum. This right here is arguably the second equation of the chapter, the first being the definition of momentum itself. This is called the impulse momentum theorem. As you can see, it is a simple rearrangement of Newton's second law. It is, in fact, Newton's second law from a different perspective. The reason it's called the impulse momentum theorem is, this right over here is the obvious part. That is change in momentum, which leads me to go, hey, note that that is change in momentum and not just momentum by itself. This is how you calculate an individual momentum. That's how you calculate its change. Okay, the left side here, this is what is known as impulse, not just the force, not just the time, but the combination of the two of them together. Okay, the units of the right side make sense to still be kilograms, meters per second. Okay, it's kind of weird to say that when they're multiplied, but that is how you say it. Kilograms, just go right into the next one, or kilograms times meters per second, but kilograms, meters per second is the right units. This, you can see, if we do the same thing that we did before, the left side's units are Newton seconds. Now, you could correctly argue that shouldn't they be exactly the same? And they, in fact, are exactly the same. If you remember, a Newton is a kilogram. Should we go off the definition right here? A Newton is a kilogram times meter per second squared. So when I multiply by this seconds, it cancels one of those to show, yes, in fact, both sides are the same. The reason why we do address different units, okay, is that it's context. When talking about momentum, You should use the units of kilograms meters per second. When discussing the units of impulse, you should in fact say Newton seconds. Again, that's not newtons per second, that is Newton seconds because they are multiplied. Okay? I'll make sure I'm looking at my script over here to make sure I hit everything. I believe I did, except for one small example here at the very end. Why is this particularly helpful? Why have we rearranged something that we arguably already know into this right here? Well, that leads me to kind of what momentum does best. Momentum really talks about collisions, an interaction between multiple different objects at the same time. Okay, so let's address real quick. Let's say I took 2 eggs, okay, obviously hypothetical, okay, or if you're Peter Pan, maybe you can see them right now. Congratulations. Anyway, we have 2 eggs. We drop them from the same height onto the ground, okay. If that was just it, hopefully you guys know the eggs break, that's it. But let's say underneath one of them, I've got a small pillow, okay, and underneath the other one, I just have the floor, just solid, normal expectations. Obviously, if they land on both, you would expect the pillow, hopefully to stay not break, and you expect the ground to crack wide open. Okay? So let's talk about that in terms of momentum. For starters, the collision in question is due to an interaction between 2 objects. So arguably, when it's falling through the air, it's free falling. That is actually a collision between the egg and the earth, but I'm not going to worry about that right now. So as both of them fall, they should both pick up the exact same amount of velocity, such that if we don't worry about exactly how big the pillow is, let's say that they hit the ground and they hit the pillow at the same starting velocity. So same starting velocity, doesn't matter what it is, it's going to be the same. Their mass is going to be the same, and their final velocity is both going to be 0, meaning both eggs in both conditions should change by the exact same amount of momentum they had. If we kind of draw it, the egg as vector as it fell, it fell. Now it has this momentum vector. Of course, it was increasing in size due to increasing in velocity. Its mass did not increase, but both of them were going like this initially before they hit the ground. Both of them stopped, so had a 0 final momentum. So both of them changed by the exact same amount of momentum. So what is different in both cases? Well, you will often find this in the impulse momentum theorem when it deals in collisions. Well, the egg that doesn't break had less force on it. Why would it have less force on it? Well, mathematically, if the right value stays exactly the same, if I want this value to decrease, then that must mean time of the impulse increased. And that hopefully starts to make sense, right? If a grocery cart is flying at you in the grocery store and you don't realize and you turn around and you just have this much distance to stop it, it's going to be a jolt. There's not that much time to stop. Whereas if you see it coming and you use your full arms to get it to stop, both cases you change it by the same amount of momentum, but due to using a larger amount of time, the second instance should require less force. Take, for example, airbags. If you're in a car crash and you didn't have an airbag, you'd run straight into the steering wheel. Now, you're going to have to stop. Using a very, very small amount of time here, let's say just making up some number, 0.001 seconds or 1 millisecond, is going to require a huge amount of force. And if you've ever heard anything about airbags, they hurt. They deliver a lot of force, but they don't break stuff as much. They don't hurt stuff as much because even if we extend that time from 0.001 to 0.002 seconds, while that's not much time, that amount of time has doubled. And if the time doubles, then the force cuts in half, which is relatively significant. Now, I think in all actuality, I think the factor is much greater for a airbag. I think we're talking at least something like 10 milliseconds. I said, yeah, that's right, 10 milliseconds, which means if I increase the time by 10, the force decreases to a tenth of what it previously was. This gives you a good idea of momentum. Now I'm going to put out another quick video on a sample problem that we did in class that you're more than welcome to to watch. I would suggest in that sample problem, if you're going to use it, try it first, because I think that you'll be surprised what you can do. And then I'll go over it afterwards. That should be relatively quick, but this is basically what we covered for the intro to momentum.